So today our first speaker is Dr. Jiyizhe Zhang. She's a new lecturer in the Department of Chemical Engineering at the University of Manchester. Prior to that, she was a postdoctoral researcher at the University of Cambridge. Her research group focuses on developing AI methods for chemical separation challenges. With that introduction, I'm delighted to hand over to Jiyizhe. Please go ahead.
Perfect. Thank you very much for the kind introduction, and good afternoon, everyone. And good morning, Lilo. My name is Yizhe, and it's my great pleasure to share our work with all of you guys today on the topic of using AI to accelerate the separation challenges. So to start with, the first question is, why do we really care about chemical separations? So I'll start from a paper from Nature a couple of years ago. So this shows calculation about the world's energy consumption, and it is estimated that around 10 to 15% of the world energy consumption is related to the separation, which is quite a lot of energy consumption, and this is in our current chemical value chain. And on the other hand, if we look at what will be the future of our chemical value chain look like, this is something that people propose for the circular economy. There are also a lot of chemical separations involved. So for example, by introducing this new sustainable feedstocks, such as from biomaterials or from some waste recycling streams, such as plastic recycling or metal recycling, these are going to be quite complicated with compositions where we need a lot of separations to extract some valuable components from that. And normally speaking, there's around more than half of the total process cost, which is quite expensive. So our group, actually only me and the master student at the moment, where we have primary interest in the separation challenges, and especially focusing on the liquid-liquid system, or broadly speaking, solvent extraction as a separation technology. And I guess most of you guys must be very familiar with this separation funnel that you used in your previous study. So what we are doing here is we have a mixture and we have some components in the system we want to separate, and then we add another layer of organic solvent or some reagents in that. Depends on the reaction or the pure solubility. You are extracting this component from one phase to another to achieve the separations. And this has a widely applications in many industries, such as chemical, pharmaceutical, critical minerals, which is very hot topic these days, and also nuclear applications, such as separating some isotopes. However, if we take a closer look at what we are having currently in the field, actually it's not that surprising, to be honest. So basically the way that we're doing this extraction research in the lab is pretty much with what we have like 200 years ago. And some of the extractant that's widely used in industry and still quite old. So they're developed like 60 years ago, 60 to 70 years ago. But if we look at that, on the other hand, these days, we see a lot of potentials using AI and lab automation to really accelerate our scientific research. And we see a lot of exciting publication and research at this moment. So we're thinking here, hopefully in future, we can also leverage this AI advances in AI automation to really help us to design some new extraction molecules, and also to run some experiments autonomously. And also, hopefully, we can design some separation process more robust and more sustainable at larger scale. However, what is actually quite missing here is basically the same problem that we see in other fields as well. So basically, we don't have enough data, and especially the data with some rich information in it. And how do we collect this data? And secondly, we also don't have some robust models. So the models that I mentioned here is not only to predict some certain properties and pure data-driven, but also some models with some physical meaning in it that we could be used for later stage to scale up this process. So in the next couple of minutes, next couple of sections, I'm going to bring you through to 2 projects that we did before to just give you a little bit flavor about what we are trying to do here. So the first one, I like to start from the first challenge that we see, which is relates to the data. So one of the key data or the key information that we cares about in this separation process is this partition coefficient. So it's defined as how much the component in one phase over in another phase, so that you can know how it distributed between these 2 phases. And we use this normally to evaluate how the separation process performs, whether it's well or not. And we use this to screen new separation system, and it's key indicator for us to scale up this process. However, the current way that we're measuring this is again by this shake-flask experiments. Most of you already done this before, and it's quite tedious workflow with a lot of dilutions, measurements, take samples from each phases and repeat that again and again. And sometimes we don't have efficient mixing, so that will generate some errors in that. And also, if we want to know what happened during the extraction process, that's also be very, very challenging because we need to repeatedly take sample from that. So the question that for us here is, how could we measure this partition coefficient quite efficiently, and how could we possibly get some rich information from these measurements? So here we design a setup or imaging platform like this. So here we have different type of measurements. We have a high-speed camera and 2 hyperspectral camera and a Raman here. And underneath we have a microchip where this is where we mix these 2 liquids together in a very small channels to make sure the mixing is very efficient. And this also sits on a stage that can move X, Y, Z direction, where you can take measurements at different locations. And in order to run these measurements, we also design a workflow to try to coordinate between different cameras. So for example, we start from the high-speed camera, where we detect what's happening inside the channel, and we check the velocity of the bubble moving in the channels, and then we pass all of this information to the next stage of hyperspectral imaging to set the parameters of the stages, the velocity of the stage, to make sure that hyperspectral imaging can happen. And we also try to automate the workflow as much as possible to reduce some manual efforts. So based on this platform, what we can get. So first of all, we could get some concentration profiles. So now it's quite easy for us to do the measurement because we just change the cameras at different locations. And secondly, it's quite easy for us to get some partition coefficients, and it allows us to compare different separation systems. So for example, this is one that we collaborate with our collaborator from Professor Nishik's group, where they designed this very interesting metal organic cages to hold some molecule inside these cages to moving from one phase to another to achieve the separations. And lastly, we can also use this as a tool to show us some local concentration information so that we can see the flow patterns without adding some extra labels in the system. And the concentration maps here also shows us the mass transfer process that's really important for us to understand what's happening in the separation system. So this is about the first challenge. And for the second one, now I'd like to take you to a little bit larger scale. So if we move from lab scale to a little bit manufacturing scale, so this is what we're going to see in the liquid-liquid separation process. So basically some devices like this. So now it's not only mixing one bubbles with another. So now you're expecting lots of bubbles here with different sizes. So normally what we're trying to do here is we develop some predictive models that can help us to predict what's going to happen in these complex systems. And the models that we're developing here is not pure data-driven ones, but most of the time we're dealing with this kind of equations, ODEs, PDE equations, and each of these terms with some physical meanings. And this term represents some phenomena that you see here. For example, the bubble is breaking up, they're coming together, and this moving, and so on and so forth. So what we try to achieve here is how could we assemble this predictive model more quickly for such a complex process. So first, to deal with this, we look at how we do this as a human modeler. So basically, we check what are the phenomena that might be in the system, and we make some assumptions, and then we develop our models and to make the predictions. So basically, what we are proposing here is try to also follow these steps, but do it in an automated way. So first of all, we try to digitizing our model knowledge. So now it's not in the human knowledge. So now it's in a digital format. And then we have some rules that we use to build these models. And then we develop some agent or automated workflow to assemble this knowledge together to become a full model. So, oops. Okay, so first of all, here we look at how we digitizing this model knowledge. So basically, what we're trying to do here is by using this so-called ontology. So try to link the model equation information here that's required for a model for a model equation, such as you can define model equations with some formula, and is associated with some phenomena. So in this way, you're putting the knowledge that you need to generate this model in a format like this, and all of this is linked together that could be later leveraged by the workflow to generate the model equations. So based on this, based on this digital workflow, so now we can move on to the next part. That's how we use this knowledge to kind of automate the model generation process. And here is an example to show you how this works. So basically, this is a example called Taylor Quid flow reactor, and people use this quite a lot for chemical reactions and also for separations. So this is where you have an internal cylinders that's sitting here that is rotating, and then you have an outer cylinder stay there. So when they're rotating, you generate different flow patterns and different phenomena in this, and depends on the conditions that you're running this process, you end up with different flow patterns that affect the outcome of this process. And to develop a model that to predict this. So here, based on the knowledge that we have before, we can develop kind of like top-down approach to do this. So basically, we are providing some initial knowledge about initial data or information of the system, like the process conditions, the geometry of this reactor. So based on all of this information, the workflow will start, and they will search in the database to see what are the relevant models, equations, and retrieve them based on the conditions that you provide, and also to compare them against the experiment data to screen this model to see which one would be the best one to describe the process. So yeah, so basically this just a very, very quick overview about what we are trying to do using AI to kind of accelerate both in the lab space, lab scale experiments, and also a little bit larger scale, how we scale this process up. So the key message here is, so now by leveraging these different type of measurements or coordinating them together, along with the computer vision model, that we can streamline the measurements and we can get rich information from the system. And secondly is when we are moving from lab scale to a little bit larger scale, so not only the data-driven approach, probably a hybrid between data-driven and model, knowledge-driven approach would be more suitable for this case. Yes, so we're a very new group, so we're looking at this AI for separation space and very looking forward to a lot of collaborations. And I also like to thank all of my previous colleagues at Cambridge, where I did most of this work within the group of Professor Alexei Lepkin. So a big thank you to them as well. And yeah, and thank you all very much for your attention.